Right, hello everyone. We left off on slide 64, so that's where we're going to start off at. So it says, note that both the stereochemistry of the reactants and the conditions, heat versus light, affect the stereochemistry of the product. And here we see that where if we go one direction, with heat, we can see how heat and light affect the product. So we left off there yesterday. It says, consider the stereochemical outcome resulting from the thermal cyclization of a pi system with 3 conjugate pi bonds. And we can get these different options. It says, note, room temperature is often sufficient to facilitate thermal cyclization. Whereas you go here, go here, go here. It needs to be up, and then if you do the same thing over here, you can see this one's up and this one's down. It says the symmetry of the HOMO determines the outcome. The outermost lobes of the HOMO rotate so the like phases overlap. So if we don't have like phases that overlap, we're not going to get, bonding. The outermost lobe, so the HOMO, and the HOMO stands for highest occupied molecular orbital, rotates so that like phases overlap. It says disk rotatory rotation. One rotates clockwise and the other rotates counterclockwise. And you can see that right here. The one's going to go this way, the other one's going to go this way, and they come in the same phase. So the outermost lobes of the HOMO rotate as they become sp3 hybridized so that the like phases overlap. And you can see this right here. This one's going to come this way. This one's going to go this way, and the like phases will overlap. Conrotatory rotation, both rotate clockwise the same direction. So this one's going to go this way. They're rotating the same direction, right? And the phases are going to overlap. Under thermal conditions, conjugated system with 6 pi electrons is disrotatory, and conjugated system with 4 pi electrons is conrotatory. So under photochemical conditions, light energy excites electron. Remember, if you have light, if we have our highest occupied molecular orbital here, And then we have our LUMO here. And if we add light, we can shoot one of these electrons up to the next level. And this will become our new HOMO, but at the time it's our LUMO. It says in this case, cyclization must occur in a conrotatory fashion. We're going to see if this one's going to be coming up. This one's going to be going down. As the same switching of stereochemistry is also observed in a conjugated system with 4 pi electrons. So in this system, we had 6 pi electrons, right? You have 2, 4, 6. This one has 4. You know, we have 2, 4. We can get disrotatory and conrotatory cyclization. Does the Woodward-Hoffman rule summarize the trends for electrocyclic reactions? So sigmatropic rearrangements, a pericyclic reaction which one sigma bond is replaced with another. You can see that right here. You can see one sigma bond is broken, but then we are forming another one. So that's just a sigmatropic rearrangement. It says count the number of atoms on each side of the sigma bonds that are breaking and forming. This is a 3-3 sigma tropic rearrangement. And they give you an example of a 1-5 sigma tropic rearrangement here. It's moving from 1 to 5. This sigma bond is formed. If we look at this one here, 1, 2, 3, we're forming that one. So cope rearrangement is a 3-3 sigma tropic reaction, which all 6 atoms in in the cyclic transition state are carbon atoms. It says equilibrium favors the more substituted alkene. So Claisen rearrangement is a 3,3 sigmatropic reaction and is the oxygen analog of a Cope rearrangement. This equilibrium favors the formation of the carbonyl bond. It is more stable than a carbon-carbon double bond. So we get this is more stable because it's more, takes more energy to break that. So we lost this sigma bond here, but we're forming this one, right? So Claisen rearrangement is also observed with allylic aryl ethers. So we can do it with many different types of compounds. Those two pericyclic reactions occur in the biosynthesis of vitamin D. We're going to break that bond. And we're going to form this. Right here, right here, right here. And then hydrogen now will be right here, which they don't show it. That hydrogen is now right here. I'll call it HA. So you got to kind of pay attention. Let's clean this up and let's just look at it again. Have all these rearrangements going on for, so first we're going to break this sigma bond right here. Then we have some bond, we have electron movement. Once we have our electron movement, now this hydrogen right here is going to end up right here. This double bond is, I'll call it A. We'll just kind of follow them. This one will be B, and this one will be C. So it's a good idea to just kind of map it out to see how the electrons are moving. All right, so compounds with the conjugated pi system absorb UV or visible light. And, you know, we all know what happens. You know, here would be our HOMO, here would be our LUMO, and we're moving that electron up. Now this is our new HOMO. This would be our new LUMO. So, you know, we use this technique called UV visible spectroscopy, and it gives us structural information about molecules. So the amount of light absorbed by a sample is a function of a wavelength called absorption. So we have absorption on the y-axis here. Absorption is unitless, and we have wavelength on the x-axis. So we're plotting absorption versus wavelength. More conjugation gives a smaller pi to pi anti-star transition. So what do we mean by that? Here we have I guess we have 4 pi electrons here, 6 pi electrons, and we have 8 pi electrons, right? And they're showing you the pi electrons. So as we add more conjugation or more pi electrons, you see this difference right here, it gets smaller. It's getting smaller. So that means it's going to be easier to go to the next transition state. So the group of atoms responsible for absorbing UV visible light is known as the chromophore. So Woodward and Phaser developed rules to predict the pi max for chromophore starting with butadiene as the base. It says the Woodward phasor rules are a guide to estimate the lambda max. And what do we mean by the lambda max? If we have our absorption and we have our, this would be in nanometers here. Here it might be the lambda max then. So this one says the conjugated iodine around 217. Two additional ones. So multiply that 2 times 30. And these are just a guideline. Again, some more guidelines. You have this table, so we can use it if we need to. So highly conjugated compounds absorb light in the visible region. So the visible region is from 400 to 700. So if we look at this right here, from 400 to 700 is the visible. Anything beyond here would be the UV. This says lycopene is responsible for the red color of tomatoes, and carotene is responsible for the orange color of carrots. So the color observed by your eyes will be the opposite of what is required to cause the pi-to-pi anti-bonding excitation. So if you're seeing blue, then what's causing this to be over here is what they mean. You just go opposite. Likewise, if you're seeing red, it'd be absorbing green. So rods and cones are photosensitive cells in your eyes. Rods do not detect any color. They dominate in dim lighting, and cones are responsible for the detection of color. So sources of 11-cis retinol include vitamin A and beta carotene. So when rhodopsin is excited photochemically, a change in shape occurs that causes a release of calcium 2+ ions. The calcium 2+ ions block channels through which billions of sodium ions generally travel each around. Just just to note that our eyes are extremely sensitive. We have this right here. And that's it. So we'll take a break. Then we'll come back to the homework. All right, we're back from our break. We're ready to get started with chapter 16. The chapter 16 homework, I mean. So we will start with question 1. It says classify this as conjugate. To classify the diene, we're going to classify this as conjugated. So question 2 says draw the curved arrow. We can do this on the same slide here. So you have this. The first one, I'm not going to draw the other double bonds, but you're going to draw the curved arrow here. And then for step 2, you're going to, so it has a positive here. Well, it's going to move. And step 3, it says draw the resonance structure. So here we're going to have to draw all the double bonds because I need to and here's the resonance structure here. All right, so we'll move to question 3. Let's complete the reaction by drawing the major organic products. The skeleton has been pre-drawn for your convenience. So hydrogen usually, so this is question 3. So when you have hydrogen and palladium, you're going to get rid of the double bonds. In this case, we're going to keep these double bonds here because they're conjugated with each other. The only double bond that we're going to get rid of then is the one within the ring because it's not conjugated. So that's our correct structure then. So question 4, it says provide the major product expected for the reaction shown, emit byproducts, ignore stereochemistry. So let me see. So MBS facilitates allylic bromination. So we're going to get 2 products. And for product 2, let's make that a little better. We get that. So we're first going to brominate, and then we're gonna get rid of that bromine, via an SN2 reaction, right? We have a strong base, so our base is going to attack here, and this will form the double bond there. Okay, we're moving on to question 5. Question 5 says fill in the pi electrons expected in the ground state. So we have 1,3-butadiene. Remember, we have 4 pi electrons here. So all you have to do, you have pi 1 and pi 2. So you're just going to put in your 2 electrons here. So we got that. It says select pi electrons. So For the HOMO, so in pi 3 you have none. So HOMO pi 2, the LUMO would be pi 3. That was pretty easy. Now we're going on to 6. This says draw the addition products form when one equivalent of HBr reacts with 2,4-hexadiene. So we have one equivalent. It doesn't matter where you put the bromine here. We'll put it right here. I mean, you could have put it on the other side, but it'd be the same thing. This says draw the 1,2 addition. So this is the 1,2 addition. And then draw the 1,4 addition. That'd just be putting the bromine on the other side. So the 1,4. Here's your 1,4 addition. All right, so we have 6 done. Let's go on to 7. It says draw the kinetic and thermodynamic addition products formed when one equivalent of HBr reacts with the compound shown. So let's do that on a separate slide. I'm just going to take a proton, be a positive charge here. That bromine is going to come in here. So this will be your kinetic product. we'll just kind of put this in kinetic. And then our thermodynamic product, if we have a positive charge here, we can move this here. There'll be a positive charge there. We can move that there. Now the positive charge is here and that bromine can come and attack here. So put the thermodynamic product, we'll just call it thermo. Double bond there. Do that. So this is your 1,2 addition, and this is your 1,4 addition. Remember, the 1,4 favors the thermo, the 1,2 is the kinetic. And we talked about that in the lecture yesterday. All right, so I think that was 7. Let me just confirm going down the list. So for question 8, it says mono addition of HBr to unsymmetrical dienes generally produces 4 products. They give us the 4 products. 2 1,2 addition products and 2 1,4 addition products. Draw the reactant diene that forms the 4 products shown. So we just have to draw how we got to these 4 different products. And that's what they want. All right, so that was 8. 9, we can do it on the same slide. It's almost the same type of question. It says, draw the structure of the diene that reacts with one equivalent of HBr to form the 2 compounds shown. So we're getting the 1,2 and we're getting the 1,4 product to get this. We need to draw this. Like I said, they show us the 1,2 addition product and the 1,4 addition, and that's how you'd have it. You'd have a conjugated diene. And it says, how is product 1 affected by temperature increasing? So product 1, by temperature increasing, the relative amount will increase. And product 2, the relative amount will decrease. Let's go to 10. 10 says 1,3-butadiene undergoes electrophilic addition. Draw the curved arrow, so we'll go ahead and do that. And do too many electrons, so we have that. This is draw both the organic and inorganic. Okay, so we'll do this. So this is step 2 now. A positive charge here, so we can jump those electrons here. Here's your inorganic compound. Step 3, draw the curved arrow to convert this intermediate into the product shown. So we'll do that. And then they have the final product, which you don't have to draw. It's drawn for you. So 11. It says consider the reaction of 2-methyl-1,3-cyclohexadiene with HCl. It says draw the intermediate. So the form of carbon tertiary carbocation. Draw this a little better. So here's A, draw intermediate B. We just move the double bond. That's all we're going to do. I don't want to show the movement, otherwise some students might get confused about drawing the arrow there, so we won't do that. But just know that this is going to jump here. Like I said, I don't want to do that. I don't want to confuse anyone. And then it wants to draw the product, so product A look like this. Product B will be just put the chlorine right there. So that's product B. So what is a major product of the reaction at very low temperature? So low temperature will be the 1,2. Under the state is the reaction under rate control or equilibrium. So the reaction is under rate control. So rate control, and this will be kinetic. There's your 2 multiple choice questions.